So once again, I want to welcome all of you to the Valley of the Shadows of this module. Today, we are looking at multiple regression. We have already looked at sample regression. And in explaining multiple regression, we'll be using a very practical data set. And all the work will be generally done in Python. And we'll be explaining the nitty-gritties, the nuances of multiple regression. Not everything, but then the main important parts as it relates to your work. I have completed the assignment. I just wanted to teach you this very one before I give it to you. Because if I have not done this one, it will be quite difficult for you to do the assignment. I must say that it's a group assignment, but it's also a loaded assignment. So I hope you have yourself in groups already, don't you? You are already classified yourself in groups, right?
Prof, please, how many people to a group?
Normally you have it already. If you don't have, then I change it. So I just want to know whether you guys have been categorized into groups already before.
Yes, we have groups for
So tell me what you have.
we have some that are 4 to a group,
And others,
3 to a group.
and others.
I think for now that's just it.
So you have 4 to a group, and then you have 3 to a group. Is that it?
Yes.
Okay. So if you,
Please, we also have 6 in a group.
that's it. So I would prefer that 6. So if you already have classification of 6 in a group, use that. Okay. So you put yourself in groups of 6. And then when you're submitting, everybody's name is in the document. You will submit both the hard and the soft copy. You will submit the hard copy to my office and my TA will collect it. The number of the TA is already in the question. Then you submit that. And then the soft copy, you do that in Sakai. And the instruction will also be there. Okay. All right. I'll be mentioning some things related to that along this line. So just hang on tight. If you do what is easy, your life will be hard. But if you do what is hard, your life may be easy over time. Most of the time, we want easy things in life. But easy come, easy go. So sometimes I tell people that don't expect things to be easy. Life itself is hard. Beat it. Beat it. Okay, so let's begin our mathematical functions. There are several mathematical functions you can do when it comes to regression. You can have a linear function. What makes the first one linear? What makes it linear is because you can see that if there is any change in the x, y only changes by what is multiplying the x. So you can see that regression normally looks at linear regression. But of course, there are other things that are not linear in life. You can have a logarithmic regression that is exhibiting diminishing marginal returns. So when there is a supposition of a diminishing marginal returns, then you can have a log. For example, if you believe that size of a company can affect the profit of the company, but then you believe that the size itself, when you are big, that as the size grows, then the profit of the company grows. as the size grows further, the company's profit grows further. But it gets to a point, size, if you grow too much, size itself starts having a diminishing marginal returns. So as you get too big, you rather have a negative marginal returns on profit. Because when you become too big, the CEOs and the management cannot monitor the people. And you tend to see this thing a lot in government sectors, where the ministries are so big and therefore inefficiencies are higher, leading to a downturn in any benefit. So there are models that can handle that. We also have polynomials. Okay? Whether you have x squared or x cubed polynomials, you can have that. You can have a regression that deals with power. Okay? You can have a regression that deals with exponential. The Cobb-Douglas production function is a typical example of a regression that deals with, powers. And you can see that the powers, when you log linearize them, the powers becomes, so when you move it from powers to linear, that means you have to take the log. So you can see in this example that you take the log of the z, you take the log of the a, that means that anything that is multiplying a with its power has to be handled in that way. And then you can look at all of the rest like that. So that is an example of, kinds of regression. Now, when do you use them? You use them based on knowledge from the literature. Okay, now let's get to our main work, multiple regression. We're going to look at the Big Math. Big Math, that's a company. It would be nice to have somebody to read this quickly so that I will use that to bring out the point. Who can read this for us? All right, I hear.
Okay. In today's modern world, huge shopping centers such as big shopping malls and marts are recording data related to sales of items or products as an important step to predict sales and get an idea about future demands that can help with inventory management. Understanding what role certain properties of an item play and how they affect their sales is imperative to any retail business. The data scientists at Big Math have collected 2013 sales data for 4,559 products across 10 stores in different cities. Also, certain attributes of each product and store have been defined. Using this data, you are to help Big Math to understand the properties of products and stores that play a key role in increasing sales. The objective is to build a predictive model that can find out the sales of each product at a particular store and then recommend to the big market sales team.
Very good. So based on this, who can tell me what the outcome variable is? Who can tell us what the outcome variable is? The outcome variable. The response variable. The dependent variable. Which variable is that? And that is even before I show you. Even before I show you, you are able to deduce this from the preamble. Okay. Settle, Samuel.
I think it is sales.
Okay. So that is sales. So now we're going to look at the data. Okay. I'm going to take you to suppose that you have your And I have to do this thing afresh, even though I've done it already. I have to do it afresh. Suppose you have your Python that you have started. The command that you can use to start, and again, I may have mismatched some of them slightly, but don't worry. I can start it afresh here if you want. The command you might use to start, if you start a brand new Python, you can use that brand new Python to even start. Okay, so let's say you want to open a brand new notebook, you can use that. The one I have just done is untitled 4. I just open untitled that. So in this untitled that, the only thing you can do is you can write this command, but I'm just copying it here. So this is your first thing, okay, to look at the working directory. So this command, import OS, and then get a working directory, will let you know where you are working from. And your data is supposed to be in that working directory, the data set. The data set is supposed to be located within the working directory. Now, if I open my computer, I want to see, hope that you guys can see my computer. If I open my working directory here, and I go to my PC, and I try to show my PC, in my case, I use my ZBook here as my working directory. So when I open my ZBook, the Big Math sales, the document is already located inside here. That is my working directory. Is that true? When I come here and I run this command, I will know that this is my working directory, and that's it. The result is saying here, my working directory is truly my ZBook. So that is fine. That's the first thing you want to be able to do. The second thing is to import all of these libraries, which I have already given you in the slides. So you can go here, and then to create a new, when you click the plus to insert a new cell, you can actually click these cells, many of them, to create more cells already before you start typing into them or copying and pasting into them. So there are a lot of packages. In fact, you do this also in your assignment. In your assignment, I even asked you to one sentence explain each package that you have installed. So this is the work, and this star here means that it's running. Okay, this star here means it's running. I'm going to the one that I've already done. Okay. So this is the working directory, and this are the packages that you have there. Now let me take you back to the bit of information about the variable. So when you look at the data set, these are some information about the data set, which I'm going to show you. But to show you that, let's look carefully at after the importation. In your slides, I've indicated that you should use this command, train_df. That's the name of the data set. In fact, you can use any name. Most will use df. And watch it. The CSV file was named as Big Math Sales. So that is the name you will type to load the data set. So once you run this command, the data will be loaded. Okay. And normally when I'm doing it in an empty shell, it makes it better, but I don't want to be copying because it will delay us. So you can see that if you type this thing here, which we just started, and then you load this data, you run this. Once you click run, the data has been loaded. But if you want to see truly whether the data has been loaded, you can look at the head of the data. And to do that, you can type the name of the data, train_df, into bracket. And that will show you the head of the data. Once I run this, okay, so in this case, it says train_df is not found because I've not added the pd dot blah, blah, blah. I'm a bit lazy when I'm typing. Okay, so you type with this. Okay, using the pandas, you can type with to command it to read the name of the data set. When you run this, it will show you the head of the data. Okay. Let me do that again. It looks like I copied the wrong one. So you bring the head of the data, and then you can see all of the information about your data. My interest is the last column here. The last column are numerical variables, and that is sales. If you check it very carefully, they are not just numerical variables. Okay? They are actually decimals. So that truly means that you are dealing with a metric dependent variable. Sometimes they are dummies. If they are dummies, then you are dealing with a logistics regression. Okay, or you're going to look at a limited dependent variable regression. So that is your major variable, the last column here, sales. For this very data set, I wasn't so comfortable with the names they are giving. You know, they could have simply called it sales. But then there are other things that they were using. So item underscore outlet sales is the name they can use. There are several things that we can find out from here. The first one, you have item identifier, which is a unique ID. You have that in the data set. That's the first thing. The weight of the product. So look at this in like, you know, Accra shopping mall, Accra mall or something. The weight of any particular product, there's a column for it. Whether the product is of low fat or is not of a low fat, that is there. Now that name alone all means that is a dummy variable. So when you check that column, okay, you will see that we have low fat, regular, low fat, regular, okay, for those particular products that you are dealing with. That shows that it's a dummy variable. The item visibility is a percentage variable. The percentage of the total display area of the product in a store allocated to that particular product. The percentage of the total display area. The type of item, the category to which the product belongs to is also there. That obviously should be a dummy because it's already a category. So when you look at that column here, the item type, if it is of a dairy product, it will mention. If it's a soft drinks, it will mention. If it's a meat area, it will mention. If it is fruits and vegetables, you will know. If it is household, you will know. Now remember, this is just giving you the first 5 rows of the data. And 5, even though the number is 4, because 0 is always counted as part. Then you have MRP, which is a maximum retail price of the data. This is a numerical variable. Okay, so when you check the data set, you will see that. Always fill your data. This is a MRP, maximum retail price. It's a numerical variable. Then you have the outlet, the unique store ID, the ID, because remember they were from different stores. So the store has got an ID. Then the year the store was established is also there. And you can see that the year the store was established is quite long written. The first store was established in 1999. The second was established in 2009. Then 99, 98, 87. The year is also shown. The size of the store in terms of the ground area covered. So is the store size, is this medium store size or it is high store size? You can see that there are some variables that are missing. So you have not available for some of the variables. Then you have the type, the location, the type of city in which the store is located. And there are several city types, whether it is a tier 1 city type, tier 3, tier 2, and all of that. The other ones. Then you have the outlet type, whether the outlet is a grocery store or some sort of supermarket. And they have been rated. So this again is a dummy. So you see that the outlet type is whether it's a supermarket type 1 or 2 or it's a grocery store. And finally, the sales of the variable, the real outcome variable that we want to predict in this case. So you keep all of these in mind, and then you can now run your command. Now, in the original data set, there were 2 data sets. We have the trained data set and we have the test data. The training data set has both input and output variables. Okay. Normally, when you are running real life, machine learning work, you will need both. Okay. But for this purpose, I've only given you the trained data set. That is why you see that it was known as train. I labeled it as train. Remember that they are missing values here. Some of the stores don't have. You saw not available for some of them. So it will be necessary to treat them before you even continue. And again, I've asked you about this in your assignment. All right. So let's take some couple of assumptions. What do we know about the variables and how are they related to sales? Well, we expect that regular fat products have a higher preference than low fat product. That is an assumption that is sensible. We also expect that the higher the visibility of a product when you enter the store, if the product is highly visible, when you enter the store, immediately you enter the store, what you see, you are tempted to go there first. So the moment you enter the store and you see maybe a new Samsung phones, you want to shiny things, you want to go there first. So the more likely that particular product is going to sell. Another assumption is that bigger stores, they see more footfall. That is, we'll have a lot of people going there than smaller stores. And so the bigger stores are likely to have more sales. Then stores in tier 1 cities, top level cities, have a higher sales because these are bigger, like urban centers. Okay? Because the people living in those cities have big incomes in the neighborhood, and so they are likely to have more sales. So sometimes when somebody is in a village, the person is not getting a lot of sales, but when the moment it comes to the supermarkets, cities, the person makes a lot of sales. The type of supermarket, if it is a type 1, they will have higher sales because of the availability of a lot of products they have. Not one product. Grocery stores see the least sales. Because grocery stores, if you enter the grocery stores and you tell them, I want to buy, say, a bicycle, they don't have bicycle. I want to buy, say, mattresses. They don't have mattresses. And then big supermarket of type 1, they have all of these. So those are basic assumptions that we want to have in this. And now we can import all the libraries, which I've already done. Okay, there. The next thing, after importing all of the libraries, which you have, and you run them one go, because we've done this before, is to check the data. And we have done this very part of checking the data. Now, you can look at not the first 5 rows of the data. Okay. You can also look at, as you can see, this command here looks at the first 5 rows of the data. If I copy this, you can look at the first 10 rows of the data if you want. So you don't use 5, but then you say 10. And then you can see the first 10 rows of the data, as you can see here. So whichever number that you want to see, you can have a look at it. The next thing is a question that I have for you here. We have to remove certain columns, and we're about to do that pretty soon. Okay. So when you go to the command here, we are going to remove certain columns, and I want to just remove them first. Then I'll ask you the question. And this is sometimes how you clean your data. So the column is train. I want to drop the column identifier for item and identifier for outlet. And you can see this column. This is the column here. Identifier for that. Then you have this outlet identifier. I'm removing them from the data set. Who can tell me why they are being removed? Why does it make sense to remove them? Why? And by the way, this command will remove them from the data set. Yes, Abrefi.
Yeah, they are non-numeric items.
They are what?
Non-numeric. They are non-numeric.
Well, the other ones too that are non-numeric, like item fat content. That one is also non-numeric. They are non-numeric. Okay. Item type is also non-numeric, but we are not removing them. Outlet size is also non-numeric, but we are not removing them. So why are we removing these particular items? Who else? I saw another hand. Or you were going to say the same thing. Michael.
Yes, sir, please, could it be that it has both numeric and non-numeric characters? So it wouldn't allow the program to read whether it's categorical or numeric.
Well, you have a point, but it must be poignant. Okay. That is a point, but that is not really the main reason why we are removing them. But that is like giving a mathematical answer instead of a practical one. Okay, so just try. Let's go to Maria.
Okay, so I think it's because those items are all unique variables.
They are all unique variables. But then if you go to item weight 2, they are the unique variables. They are the unique numbers. Like 9.3 is different. It's not shown everywhere. So they're also unique. Okay, they're also unique. Selassie, it's something or
Doc, so I would say that they don't make sense if you are using a regression and you are using that. It wouldn't make sense in your data, so you have to take them out.
Perfect answer. The rest are good, but this is perfect. Because you know you're going to do a predictive model or a regression model. And therefore, regression model, all you need are your independent variables and your dependent variables. And when you look at this, there is nothing independent variable about them. And there is nothing dependent variable about them. If you look at item for weight, yes, it's numbers. And therefore, it should represent either dependent or independent. If you look at this one, it's a dummy. So that is why the guy who said that they have both numbers and letters, it's okay, and they have unique things. But there is no meaningful attachment to them. It's not going to affect the entire data. It's going to affect only that particular store. And that is why we are dropping them. There we go. Okay. I like it when you actually comment, when you talk like that. So now that we have removed this information, the next thing we want to do is, so I asked that question here. We now want to look at the information about the data set after we removing them. And to do that, you run this command here. Okay. So let's go to the next command. You run this one here. And there you go. Look at the information you have about the data. So tell me, regarding this data set information here, look at it very carefully. There are a lot of questions that are here. Okay. The first question is this. Which variables are numerical? Which variables are nominal? Which variables are ordinal? Okay. So let's first go to numerical. Based on this information, what do you see? Quickly, you can tell me numerical variables. The names are all shown here. You have 12 different variables here. Variables are numerical. Give me one variable that is numerical. And what gave you the clue that is numerical? Johannes.
Doc, so I'd say item weight,
Good. What gave you the clue that is numerical?
because the data type showing at the last part shows a float.
Exactly. Very good. Which other variable is numerical, Priscilla?
Doc, item visibility.
Okay. And the keyword that gave you that is what? It's a float, right?
Oh,
64.
yeah.
Okay. Which variables are nominal? Which variables are nominal? Now remember, I did not say ordinal. Yeah, this is tricky there. Okay. Which variables are nominal? Nominal. Nominal, not ordinal. Nominal. In fact, when you look at the columns, you see. When you look at the columns up here, you see somewhere.
Item identifier.
Item identifier. Okay. All right. I don't know, but we removed that column, right? So let's assume that column was still removed.
Okay, so please scroll so I can see.
Sorry?
I wanted to see the outputs in the previous.
That is the output I'm showing you here.
Okay.
All right. So let's look at this variable. You see, the nominal variables are those you cannot rank. So when you look at item fat content, you have low and you have regular, and then you have other ones. Okay, that is it. Now, if you look at item fat content here, now I'm going to show you something interesting. What is that? Item fat content. This one here is an object here. Okay, object here means that they are categorical, but categorical are of two types. It's either nominal or ordinal. And when you look at item fat content, you cannot rank them because some people may like regular fat, some people may like low fat, some people may like high fat. There is no ranking of importance, and that is a nominal part. But that is not the, in fact, another nominal one. Okay, based on this, you should be able to tell me another nominal one. Okay. Item fat content is the one I've given you. Apart from item fat content, which other variable, dummy, categorical, do you think it is also nominal, apart from item fat content? Given the explanation of nominal that I've given. Let me see if somebody is cracking here. Yes, Lassie.
You said the item type.
Item type. Very good. Item type here. Okay, because you cannot rank them in order of importance. Dairy, soft drinks, meat, fruit, vegetable. You can't rank them in order of importance. Okay, we are not doing dietetics here, but generally you can do that. So that is good. That is another variable that is nominal. Okay, would you say outlet sales is nominal or ordinal? Outlet sales, is it nominal or ordinal? What would you say? Samuel?
I think the category is outlet size and it is ordinal.
Yes, sorry, outlet size. Yes, it's ordinal, okay, because you can rank them. What about outlet location type? Outlet location type. So all that we are doing here is that we are filling the data, and you always have to fill the data. The data set I'll give you, you have to take your time and fill it. Okay. Outlet location type is also ordinal. Outlet type is also ordinal. Okay. So those are the things that you got to take note when it comes to all of this. Now, we already did say that some of the variables have got missing values. Okay. So, and you want to check if there are missing values in some of the variables. So when you go to your slides, I have some information here. By the way, I have some information here. Yeah, I think the other one, I was using the other code. So that is why one of you mentioned item. We had 12 variables, but now we have the actual 9 variables because I removed the identifiers, the item and outlet identifiers. So you can now see the proper one. So if you want to see, if you go to your, oops, if you go to your notes, I've indicated some things here. Oh, by the way, if you look at the data, I have some questions here. How many observations and columns are there? So looking at this, how many observations are available? You can tell me. Looking at this on your screen here, how many observations are available? Abrifi.
8522.
Good. And which ones have missing values? And how did you know they have missing values? Just looking at your info. Arthur.
Sorry, I wanted to say it's 8523 instead of 8522.
Oh, she said 8522. Okay. Priscilla.
Yes, those that have missing value is item weight because the number beside it is 7060 instead of 8523.
Okay.
And outlet size because its number is 6113 instead
Very
of
good.
8223.
Excellent. Excellent. Perfect answer. So now that we know those ones are the ones that are missing values, we can look at this next command to check the percentage of missing values they have. And of all these variables, which one has the highest percentage of missing values? You can see that it is outlet size. It has the greater percentage of missing values there. Now, on the basis of this, we can now go ahead and then show the next level of information. I want to run through most of these things so that we do not delay that much. Because if I try to copy and paste, we are going to delay. So let's have some quick flip of our data, a look of some of the data. So the first thing we're going to do is to show a box, a bar plot or a count plot of the item type. Okay, the item type. Now, if you look at the item type here, and again, you have these slides that you are to copy. So if you look at item type, there are several information that are there. And once you do the item type, because one of the things about item type is that it has so many categories, so many than any other one. And yet those categories are not really rankable. I mean, naturally, you cannot really rank them. Okay. So what can you say quickly about, because I have some of these things in your assignment, what can you say quickly about this item type? Looking at the graph that you're showing, the count plot, the frequency graph, what can you say about it? Anybody? What can you say about this graph? What comment can you quickly say? Well, you can see that the vegetables are the highest, and then you have the seafood as the lowest in there. And there is a trend of movement, towards, there's a slowdown of movement. But the key point you can say is the highest and the lowest that you can see there. Let's quickly analyze other categorical variables. And then graphical analysis is very good. So I have indicated that you should show a lot of graphics in your work. Lots of graphics in your work. So one of the graphics you can show is for outlet type. So this is graphic that you can show. Okay. This is one graphic that you can show. I decided to use kernel density graph. And looking at the current density graph, which one has got the highest peak? Which supermarket type, outlet type, has got the highest of peak? Arthur?
The grocery store.
Well, check it very carefully. It is a grocery store. Okay? It has a highest peak. But which one has got a very high density? A very wider density. Not too plasticatic, but then it's got a very wider density. You should be able to know some of these things. And again, you should read some few information regarding this because I have set questions like this for you. Kernel density estimations. Yes, Samuel.
Supermarket type 1.
Very good. Yeah. Kernel density estimation is a very fine way to have a feel of your data. Okay. Another thing you can do is compare some of the items. So in this case, I decide to compare using the SN plot. And you can do the same thing. When you run the SN plot like this, you get this, which is a box plot of the location type across sales. So based on this, you can see clearly which location type has got a higher sales. And again, this tells you that the location type are only 3, tier 1 to 3. All of them have got outliers. Comment on the outliers. All of them have got outliers. Okay. They all seems to be having a similar median. If you check it very carefully, they all seem to be having similar median in there. The median is the center of the box, and they all seems to be exit. Tier 3 seems to be having higher than tier 1 slightly. Tier 2 seems to be having higher sales than tier 3 slightly. But again, the graphs appears to be, showing similarity. So one of the best things you should do is to test statistically whether there is a difference. And you have those tests to do also in your assignment. One of the tests to do, once you prove that this data set sales is normally distributed, then you have to use the independent ANOVA test. But if you prove that sales is not normally distributed, then you have to use the Kruskal-Wallis test. Take note of some of these things. Write some of these things down. They will become useful when you're doing your group assignment. Okay. The next thing is to show a histoplot, okay, or a Violin plot of the data set. Now, I'm going to show a histoplot together with a kernel density plot of the data set. So there you go here. Okay, I'm going to run this command just to show you. So watch it very carefully. I'm showing it for our location type, the same location type above, but I'm showing a Violin plot here. Now, there's a difference between Violin plot and kernel density plot. Violin plot does not only give you the center of the distribution. It doesn't only give you the center of the data. You can see the Violin, the box plot is giving you horizontal line, which is the second quartile or the 50th percentile. That's the center there. It doesn't tell you much about the distribution. Look at the box here. That's it. But then if you look at the Violin, when you turn it the other way around, when you rotate it, 90 degrees, you will see that there is the distribution. But of course, the center is also there. So you can see the center is a dot, the white dot, the same thing the box plot is giving. But then it also is giving you the distribution of the data. So there's a high distribution of the data within those in the tier 3, than the rest. And then, of course, any pointed to there also exhibits outliers, just like the box plot is exhibiting. Compare these things, read around these things, and have a feel of how these distributions are very good. When you're doing your thesis, your dissertation, your project works, all of these things, you will need them as well. So it's not only for this module, but it's also for your long essay or thesis or dissertation. Another thing you can do is you can also do line plot, multiple kernel densities, okay, like what you have here. So if you run this one here, Okay. I've done a similar kernel density, this time not for the location type, but for the outlet type. And you can see that the grocery store is showing a higher peak of the data, but it's very, very nucleated among it themselves of sales. Okay, so this is in line with sales. Remember, sales is the outcome variable. So you have a lot of things that you can show when it comes to sales. So all of these are things you can do with the data set. Now let's go to a description of the data set. All assignments, you have to describe the data set. By that I mean you have to have the mean, the median, the mode, the maximum, the minimum, the 50th percentile, the 75th percentile, the first quartile, all of those things. We've done this thing already. Once you use this command, it will give you a complete, it will give you a complete information about the data. But there's something very observable here. And I want one of you to tell me, instead of doing something, the result gave you something. Who has spotted that? Instead of doing something, the result is giving you something. Who has spotted that? Watch it here. Look at the description of the data. The result is rather giving you something instead of giving you something. Exactly, Frederick. They are only numerical values. So descriptive statistics is showing only numerical data. Is that sensible? Is that sensible? It's showing only the numerical values. Is that sensible?
Yes, Doc.
Good. Why? Why? Oh, you said yes as a lottery. You said it as a lottery ticket. Because if you're not able to tell me why, it means that you took a guess.
Doc, I said yes because with categorical variables, you cannot get a mean, median. Maybe you can get a median, but you cannot get a mean and all of those the descriptive parts on them. So it's better to use numerical values.
What if you can? What if you can get? Because I can get. If I was using R software, I could get.
So, but it wouldn't make sense.
That's the word. That's the word you got to talk about. That is the key, powerful, remarkable word that you use. It does not make sense, even if you get them. So the key is not because Python is not giving us a result, but the key is because they are senseless. You can't take sex type, male and female, and tell me that the average of the sex type is 0.4. When one is 1, 1 is 0, meaningless. So that is why the categorical variables here are wonderful, not to bring, but the numerical ones have been brought. Okay, now focusing on the numerical ones, the count here talks about what? You can tell us. What does the count here refer to? I'm asking you questions that I will ask you later. So I'm giving you answers that you will get later. What does a count here mean? Is a number of observations. The mean is there. What is one thing that it did not give us? What is one thing that would have been nice to get, but we didn't have? One thing. If you look at descriptive statistics in particular, there are one particular things. Oh, someone says the mode. To be honest, the mode is not really that important. But it's one or a couple of, exactly, the median is key, but it didn't give us a median. Okay. The median is key. But the good thing is that other things are also key, but they didn't give us, but you can get it on their own. For example, the ketosis and the skewness. It didn't bring them here, but you can generate them yourself. Okay. The median, you can generate it yourself. But when you look at descriptive statistics, the mean, the standard deviation, the minimum, and the maximum, these are the key ones that you need. These are the very key ones that you need. Okay. Now, the skewness, you can use this command to generate the skewness yourself. So if you want the skewness of a particular variable, let's say that I've done the skewness for MRP. Okay. Yes, Samuel.
Sir, please, talking about the median, can we use the 50th percentile to spread?
Yes, you can. Exactly, perfect. You can use this one to represent the 50th percentile because it's also the median. Okay, very good, very good. But it looks like I hear a lot of echo when you talk somewhere. All right. Now, you can take any item and find the skewness. And you can take any item and then find other things. So I'm just picking on sales, okay, and just drop sales here. And you can see that the MRP, the skewness was 0.127. If I run the same thing for sales, the skewness is 1.17. So you can see that you can get the skewness for any other particular variable that you want to have. And then, of course, you can have the other item. The most important thing is get what they mean. One of the first things is that if the standard deviation here is bigger than the mean, it means that there's a lot of variability in the data set. If you check sales, sales is 21, the mean is 2181. The standard deviation is 1706. So the standard deviation is not bigger than the mean of sales. So it means that the variables, observations are closer to each other. They are not wide apart from each other. That's what it means. And normally you will see that that is so when you even have the range. Unfortunately, the range is not here, but you can use the minimum and the maximum, the difference. Okay, you see the minimum is 33.29. The maximum is 13,086. You might think that, ooh, that's a big gap. That's a big gap. It means that there's a wide, some are very big sales, some are very small sales. Well, the standard deviation clearly shows that that is not really the case. Okay. That is not too really the case. But in fact, the standard deviation is closer to the mean. Okay. So it just shows that a modicum of that is evident. You can use pair plot to do some comparative analysis. I will leave you to explore that on your own. Pair plots is one interesting thing you can use to do some comparative analysis. Okay, so try and look at pair plots by yourself. Okay, all the graphs that we did are in your slides, and you can see some of these things. I did not show all of them, but you have all of them in your slides. The next most important thing is to check for correlation, because remember, you're about to do a regression. And so you need to know correlation. Correlation is about association. Regression is about causality. So let's look at association first. Okay. By the way, this is a pair plot. So one of the things you should learn is you should have a category of the variables in your life. You should be able to know categories, contingency table for different categories. This is very important. So when you look at item fat content, for example, there are 5 levels: LF, low fat, regular, low fat, and REG, things like that. You have some acronyms for that. And then for the outsize, you have high, medium, small. High, medium, small. You can check how many of the observations have regular and high, and that is 313. How many of the observations have low fat and are small size? And they are 29. And this is known as contingency table. You can create a contingency table between any 2 categorical factors. I have asked this in your assignment, that's why I wanted to know. And you can use this command to be able to create that contingency table. Take note of that before we go to the correlation. The correlation, you can use a heat map, as most of you may be aware. You can use a heat map to generate the correlation, and it will give you the correlation of only the numerical variables, because there is no need to find the correlation among categorical variables, or even between a numerical and categorical variable. It doesn't make any real sense, once again. because it will give you values that are multiple. Because the categorical variable has got multiple levels. The dummy has got multiple levels. And so you don't know which level is driving that collinearity you are talking about. So it's always good to focus on only the numerical. This information I've asked you as well. This very point I made, why that is so in your assignment. So if you generate the correlation matrix, you'll get this result. And you can see that there's a correlation between each numerical variable and the other numerical variables. Based on this, you should have some comments you can make on the work. Okay. So look at this very carefully and answer the following questions for me. What is the correlation coefficient between visibility and MRP? Who can tell us? What is the correlation coefficient between visibility and MRP? Visibility and MRP. You know, we've looked at correlation last time. So now tell me the value, the coefficient between visibility and MRP. Very good. You have negative 0.0013. Okay. Visibility is here. Okay. MRP is here. It's very, very low. What do the colors signify? You can tell me, what do the colors signify actually? The colors, what do they mean? Selassie.
So the one with the, I don't know if it's white or creamy color, shows a higher correlation.
The one with the one.
The one, yes, the one with the cream, or is it cream or whitish color?
Shows
a higher correlation among.
The word is perfect. Shows perfect correlation. Perfect. And you're right. As you come, the legend will tell you on the right here. As you come down towards black, very black, from the creamy white area towards black, you are reducing the correlation. Okay. And when you are in the middle, the red area, it is high. Getting towards white is even highest. And then pure cream, in this case, is perfect. What does this mean? Normally, we want a very strong correlation. Remember, our focus is on sales. So you got to focus on the sales variable here. That is the most important one. And when you look at sales, the variables that are highly correlated with sales is just item MRP. And even that one is a very moderate correlation with sales. So majority of the data are not showing a strong correlation with sales, which is our outcome variable. And that is one quick thing you want to take note. But I have a point here, because you see, telling me something is correlated is one thing, but telling me whether the correlation is significant is even better. Okay. So you need to be able to check it. Anyway, the other ones are showing negative correlation that are not that strong. You can use a scatter plot to generate the correlation between sales and any of the variables. Scatter plot can do that as well. But I have some few things here. If I were to pick some variables that are multicollinear, which one can I use? Please note, and you might want to write this, multicollinearity exists when two independent variables are so highly correlated that it becomes difficult to disentangle the partial effect of one from the other on the dependent variable. That is the definition of multicollinearity. Multicollinearity happens among independent variables alone. So we don't need to look at the sales. Sales columns is out. Every other variable among itself, if the correlation is so high, we'll come back to how high is high. If the correlation is so high among these four other independent variables, then that may signify multicollinearity. And you don't want multicollinearity to be that high among independent variables. But you want them to be high between dependent and independent, but not among independent. So if you are to identify 3 pairs of variables that may have been multicollinear, then you have to look at these numbers and look for the highest ones. And when you look at these numbers very carefully, the supposedly higher one is this. Let me see. Okay. This one. I mean, they are not high at all, but if you were to pick the highest multicollinear pair, it would have been outlet establishment year and that of item visibility. But that's the only one showing the possible highest value. Forget about numbers, forget about the sign. The negative or positive is irrelevant, okay, when you are determining the strength of the correlation. Very good. At this one, it seems that there is not much issue about multicollinearity. Now, to get the significance of the correlation, okay, this Python doesn't give much of the ways to be able to get that at a go. R can give you the significance of the correlation very easily, and you can use the R to do that as well. All right. Now we are going to clean the data very quickly, and then we can proceed with our analysis. So, now one of the things you can do also is that before you clean the data, you should know that you can check whether some of the variables are normally distributed. Okay. And I want to check whether a particular variable is normal. Okay. To do that, you have to import this Shapiro test from SciPy. When you run this command, and I'm giving you this because of some of your assignments. If you run this command, and you can check whether sales is normal, normally distributed. You can use this command to run whether sales is normally distributed. Let me run that. And when you do that, you can see down here that there is a statistic of 0.909 and a p-value of 0. When you have a p-value of 0, it tells you that the variable is not normally distributed. I mean, when the p-value is below 5%. So it tells you down there that the sample does not look Gaussian. Gaussian means normally distributed. It doesn't look Gaussian. It doesn't look normally distributed. So you should reject the null hypothesis. The null hypothesis says that that variable is normal. The alternative hypothesis says that the variable is not normal. And in this case, with a p-value being less than 5%, with a p-value being actually 0, which is less than 5%, it means that sales isn't that normally distributed. If you're doing practical work, you got to do something about that. But that's for later time. So that's how you check for normality. If you want to use a graph to even depict the normality, you can use this graph, and that's what I've run here. So when you look at the graph carefully, a normally distributed graph is normally like this. It goes here, very high, bell-shaped like this. But this one, you can see that it's very skewed, depicting what the p-value said, that is not that normally distributed. You can use this to check for every other variable. So that's for you, whenever you want to check for normality. Now, let's check for the missing value, the variable that had a missing value. You use this command, and then you can see that item weight has 1,463 missing values. And outlet size has more than that. We knew about this already, but we knew about them in percentage. Okay. So, and this is called data cleaning. Okay. So you can see that these variables, we got to handle this one. And this is a tough work. There are many ways you can handle this. I'm going to move a bit faster here because this is all my focus. But this is for your project, when you're doing your project. So it's very important that you know it. you can impute, you can use something we call interpolation. When you Google it, you know, interpolation can help you to fill in the gaps for the missing values. You can use the mean median mode, you can use the k nearest neighbors. Okay, all of this you can use that to fill in the missing values. But here, what we are going to do is we're going to try to find out some link between weight. You see, the weight is one of them that has missing. Between weight with the other variables in the data set, you're going to find some association between weight and the other independent variables. And then we'll use that to find the missing values. After you get the missing values, the overall distribution of the data should be checked, and it shouldn't change significantly. Because once the distribution should change, it means that what you have done is that you have punished the data, because you have brought some foreign materials into the area. But as long as the distribution is fine, it is not changing significantly, your approach is good. So how do you do that? We decided to impute the missing values using the uniform distribution approach. We chose a parameter of A being 10 and B being 14. And these are all based on the approaches there. I chose this thing. I cannot go into the full details because that's not the main concern for our work here. Okay. And then I use that to generate the missing values here. So you can see that the random uniform distribution of 10 and 14 are used to calculate these ones here. And we use patterns from the variables outlet type and outlet location type. Remember, we are using other independent variables to help solve the problem for weight and size. So we use that to compute the missing value for outlet size. So that's for size alone. We are using type and location type to handle size missing values. So this is how we did it here. Okay. You run this command, okay, and then you create that. You do for this, and then you do for that, and then you run for this one too. And in each case, and that's for size, by the way. We come and check for the missing values again. And you can see that now, item weight missing values is no longer what we saw here. Okay. And then size missing values is no longer, like that. Missing values are all 0 in all of it. That's the point I'm just trying to say. I don't want to go into the nitty-gritties of all of this. It will delay most of our time. And everything that was done here, I've commented here for you. So we will update the information we have, okay? And then we can see from this that the missing values are now 0. Now, one more thing is called feature engineering. And we will use that feature engineering to create a new feature for some of the variables. And please watch something very important here. We are going to hypothesize that as the store gets older, remember that we have a data for establishment. As the store gets older, sales will increase. So using the establishment year and this data, the data was collected in 2013. So you look at establishment year, you subtract the establishment year, let's say 1987, you subtract that from 2013. So the age can be found by that subtraction. And that's what we are going to do to create a new feature from the existing features, the new variable from the existing variables. And you are going to see why we are doing that, because you're going to use that to create some dummies as well. So we are going to do that to show for the age outlet. And again, I'm running slightly with this because that is not my major thing. This is just to create some of the few things that I wanted. We box plot the sales by the age. Okay. And then this is what we see there. So you can see that we have a bit of box plot of the sales with age. Then we can now remove the variable outlet establishment here. because we've created a new variable called outlet age. Okay. This command will remove that. And finally, we can extract the dependent variable. Okay. And this command does that. And finally, we can now show the head, the dependent variable here. And all that I did, I'm going to show you here to explain what I did, because it's quite a lot of things I went through. When you look at the new feature we have created, our hypothesis doesn't look like a hose when you look at the plot, because there are different ages of stores and the sales have got similar distribution approximately. So we don't have any big issue because the distribution has maintained. And we said that as long as you maintain the distribution, there's no problem. We also remove the targeted variable, okay? After creating the outlet age, we remove the targeted variable and extract a new outcome from the targeted variable. Now, please note that the data I will give you, you will not do any of this because I've done all of them for you. Okay? So just take this thing for your normal project that you sometimes will do. Okay, so we extract a new outcome variable, which is what you see here. So the outcome variable sales, we've extracted a new one from that. And look at it here. Look at it. We still have our items here, the numerical variables, the outlet age. See that we brought that in there, okay? Because it was establishment here, but we've now called it outlet age. And then we've also created these ones. Now, what are they? These ones, we've created dummy variables for each of the variables. Check it very carefully. You see that they have 0, 1, 0, 1, 0, 1. Okay. That is why sometimes I like R. R will keep it them as they are, you know, and then we'll pull out the results automatically. But this one, we are creating them. So for each item type, we are creating a dummy for each one of them. Now, when I say dummy, we are creating a value of 0 for that particular outlet and 1 for that particular outlet and 0 otherwise for all the others. We do the same thing for all other dummies. Dummies for outlet type, dummies for location type, dummies for, so we created a lot of dummies here. This is now our new variable. The columns have increased, okay? But that's okay. We've done that beautiful work so that we can now use that for our regression. So we created a dummy and you can see the codes that we did, all of them are here. The overall number of columns have increased, like I said, okay? But we've been able to remove the categories and dummy size them in this regard. Now, finally, we can scale the numerical values to have the same range. If we don't do that scaling, the model will be biased towards higher numbers. We use something called minimum max scaler, you know, to handle that. And again, like I said, in your normal data set, you will not have to deal with this, so don't worry. So we use this command. It will give a return of the data in an array form, and then we'll convert it back to pandas data frame. Okay. And then we can now go ahead and use it for our regression. I've done all of that here. So I'm going to run these ones, show that one, and now we are ready to run our regression based on the complete data set. So this is going to be our regression command that we are going to use. This is the final training skilled features that we did. To do the regression, we are going to run this OLS, the one I just zoomed. We are going to call it OLS model _ 0. We are going to use ordinary least squares, and we are going to have this train target as our dependent variable and train features scaled as all the independent variables. This one. And then we will fit the model and show the results in that regard. And then we'll print the results out there. So I'm going to do that here. Okay. Just running this will give us everything that we need. This is the most important thing for today. Okay. Now, let me show you the assignment, what I will give you to just give you a feel of this information that I said I'll give you. Because your information will not need any of this. Okay, I have done all of that. So I just give you the data set. And all you are supposed to do is to use that data set to be able to come out with the information that you need. Well, I think that you are not able to see. Let me just share the entire screen. So I'm opening an Excel for you. This is going to be your data set. I've cleaned it all for you with all of this. So you can see that. Please confirm if you can see my screen.
Yes, we can see.
Okay. Don't worry. All the preamble that you need for this, you have it there. So this is like COVID-19 wearing of masks. So the dependent variable here is wearing masks. And wearing masks depend on several things. It will depend on several things. All of these numerical variables, it will depend on them. And they've all been explained in the preamble. It will also depend on the educational level, the ethnicity, the gender, the religion, the employment type of person, all of that. So you have these categorical variables, and the levels are there. All of these have been cleaned already. Okay, so you don't have any wahala to do the cleaning. Once you have this, you can run the regression I'm asking you to run, which in this very example is this. Okay, so once you use this code, of course, you have to edit the names. Once you use this code, you can now run your regression, and this becomes your regression output. It is from here you have to address several questions that will be posed at you. But the key point is that in our example here, all that we were looking for by dealing with missing data, dealing with cleaning, adding some features, removing some features, all of these is to eventually get a data set like what I've already done for you. And now yours is to now make sense of this. Okay, so let's go back to our sales. Now we've been able to get a regression result. The regression results gives us two parts. So look at the results here very carefully. It gives us two parts. Guys, there are issues with this regression, which is good issues. Like there are problems, but these are good problems. One of the first things you will note when you get a regression in Python is to get a feel of what you've done. So the first thing you get is the dependent variable. The model that was used is the ordinary least squares. The method was actually the least squares method. The date I did that is today. So you can see that today's date is there. The time I did that is 8:17 a.m. It's now 8:20. So some few minutes that I did that. The number of observation is 8523. The degrees of freedom of the residuals is that. And for the entire model is this. The covariance type is non-robust. All of this, you learn them later. One of the key things in a regression is to check whether the model you did is correct, and you use the R-square for that. We've done most of these things when we're looking at a simple regression. So the first thing I want to ask you is the regression model reliable? Is a regression model well fit? Is a regression model good? And if you want to tell whether the regression model is good, you got to use a particular statistic. What statistic is that? If you want to tell whether the regression model is good, what statistic do you use? Several of them. But the key one is R-square. Now, the R-square will tell you whether or not the regression is good. The R-square in this case is 56.3%. You can see that. Which means that 56.3% of the variation in sales has been explained by all the independent variables. Is it good? Some people suggest that as long as it's more than 50% is always good. Some people suggest that when it is 80% and above is good. Some people even say that when it is 0.3 is moderately good. I will tell you that you normally have to justify this together with the independent variables. But what you are having here shows that a regression model is reliable. What is the difference between the adjusted and the R-square? The adjusted penalizes the inclusion of irrelevant independent variables. So if there are some independent variables that are not relevant, but you still include them in the model, the adjusted R-square will come down. So most of the time, the adjusted R-square is lower, slightly lower, or even lower. If it is really lower than the R-square, it means that there's a lot of irrelevant variables you've included. In this case, they are similar. So the regression model appears to be reliable. There are other statistics that will determine the performance of the model. And one of them is a log likelihood value, the Kaike information criteria, and the Bayesian information criteria. What are they? Well, the log likelihood, as you can see here, measures the goodness of fit, the fitness of the model. Higher values show better model. But it is not that good when you're doing one model, because higher values show better. What is higher? How high is high and how low is low? So when you have two models, two regression models, so maybe you run the regression model for those that are women, you run the regression model for those that are men. You compare the log likelihood and you see that that of the men is bigger than that of the women. Then you can conclude that the men one has got a better model than the women. So when there are two models, that is when the LL is used. Next is the BIC. The way you calculate it is here. The software does it all for you. Okay. Now, if you look at the K, it tells you the number of the parameters in the model, which includes the intercept and any other extra predictors. The log of the N will tell you the log of the sample size. Both the AIC and the BIC act just like the R square. But then the BIC punishes more for including the independent variables than the AIC. Okay, so usually that is what you get, and you can have a situation for that. Again, remember that all of them, it is when the models are two that they become useful. So take note of these values that you are seeing there. Now we are left with the F statistic. The F statistic is 365%. Its p-value is 0. Remember, the last time we said that the F statistic tells you whether the independent variables are jointly significant in influencing the dependent variable. Combined, are the independent variables jointly significant? And when the p-value is less than 5%, it means that they are jointly significant. When you look at our p-value here, is it less than 5%? Yes, look at it here. So it means that the independent variables are jointly significant in influencing the dependent variable. That is an F test. Now, let's go to the entire data result, the actual work. It tells you about each independent variable. The coefficient of each independent variable is here. The standard error is here. The t-value is here. The probability or the p-value is here. And then the confidence interval is there. Guys, this is the key thing. I just want you to know that the coefficient, let me delete this first. The coefficient divided by the standard error should be equal to the t statistic. So if you take this value here for item MRP, 3,666 divided by 46 should give you 78. That's always something you should note. You will do a lot of interpretation with your exams as well as with your assignment. It's going to be a compulsory question. So it's very important that this regression work, you have a clear understanding. Now, remember that the item type, there were several of them. We classified them, okay? That's why we have to change them and dummy-size them. But I said that R does it automatically for you. You can see that all of these ones here are item type. They are all item type. You see, they're talking about the same thing here. But then they are in dummy. So based on this, you'll be able to check which independent variable are significant or are not significant. But let me tell you a little bit about that before I come back here. There is an omnibus test here. Let's talk about that first at the bottom. Okay. At the bottom, you see there's omnibus value. There's a probability of omnibus value. There's a skewness, ketosis value. There's Debin-Waston value, Jacobera value, probability of Jacobera value, and the condition. See, all of these things, you have to have a feel of them. And that is my interest a bit before I come to the main one. Okay, so what is the omnibus? It tells you, or it measures if the errors are normally distributed. The probability of the omnibus value, if it is close to 0, that is good news. Sorry, if the probability is close to 1, that is good news. But if the omnibus value is close to 0, that is also good news. So if you look at the omnibus value, that is not close to 0. The probability of the omnibus value is supposed to be close to 1, but that is rather 0. Okay. So the good news is if it is 1, if the probability is 1, that's much preferred. The skewness, the value of the skewness is preferred close to 0. Now, if you look at our skewness here, okay, it's not that close to 0. Okay, but that is what you want. It will tell you that the distribution of the residual is normal if it is close to 0. We'll look at diagnostic text later. The Debin-Waston is another one. So you can see the Debin-Waston here. The value is 2.004. What is that for? A test for homoskedasticity. The last time we looked at assumptions of regression. And we said one of the assumptions of regression is that it must be homoskedastic. The errors must be homoskedastic, which means that they must have a constant variance. In other words, the errors must be independent. Now, a value between 1 and 2 for the Debin-Waston is good. When you check the value, is slightly above 2. So that is something to really check. Could it be that there's a bit of heteroskedasticity in this? We'll see. Then you have Jacobera test. Again, it tests for the normality of the residual. Check it out. All of them are looking at the normality of the residual. And by the way, you will see that everything about this regression is about the residuals. We did it the last time with a simple regression where you minimize the error sum of squares, and in the process you get a coefficient. So this Jacobera tests the normality of the residuals. One of the assumptions of regression. It's called after the guy Carlos Jackie and Anelbera, and it's always positive. Bigger value shows that the errors are not normally distributed. Now, when you look at ours, okay, you can see that we have bigger values. So could it be that the errors are not normally distributed? So you need to be able to find out all of these. Now, we are going to find them out properly by looking at these questions. Which independent variables are statistically significant? Now let's go back to the result. How do you know an independent variable is statistically significant? Check the p-values. Once you check the p-values, you will be able to know whether an independent variable is statistically significant or not. When the p-value is less than 5%, when the p-value is 5% or less, it means that independent variable is statistically significant. So I want each one of you to tell me which independent variables here are statistically significant. Mention any one of them that you think is statistically significant. Let's start with item weight. Is item weight significant? Yes or not significant? No. Who can tell us? No. Very good. Item weight. Yeah, Priscilla.
So I was going to say it's not significant.
Good. How about item visibility, Priscilla?
It's also not significant.
How about item MRP?
Yes.
It's not significant.
How about item MRP?
Yes.
MRP is 1, 2, 3, yes, 20%. It's not
Yes, it is.
significant.
Less than 5.
How about item MRP? You see the way I've repeated that?
Let's see. It's 0. Okay, it's significant.
How about age?
Age is also significant.
How about item fat content regular?
Not significant.
Okay. How about all the item type?
All of them up to this one, 8.2. Item types touchy food. Yes, they are all not significant.
Very good. You understand what you're doing. How about item size? I'm just putting them together.
Yeah, they are significant.
And how about location type?
Location type 2. Location type 2 is not significant because it's a little bit higher than 5%, but then location type 3 is significant.
Very good. And how about outlet type?
The supermarket is all significant.
Very good. So guys, you should be able to learn all of this. This is what we mean by whether or not something is significant or not. Okay, she's been able to walk us all through. If you don't understand anything regarding significance, you can always see her and she will tell you. That's what we mean by determining the significance. Now, next question. Are the coefficients jointly significant? So let's go here. Okay. Are the coefficients jointly significant? Who will answer that? Who will answer that? Are the coefficients jointly significant? Raise your hand and talk to me now. Unless you are afraid of, I'll ask you, why did you say so? Yes, someone.
I think they are jointly significant.
Why?
I'm looking at the F statistic is high with a significant probability.
Good. All right, so that's it. Okay, you should be able to dictate all of these things. Now let's look at quickly interpretation. So we are going to interpret weight, age, small outlet size, outlet type, and supermarket type. Now these ones carry a lot of marks in your both assignment and exams. Okay, so you should learn how to do interpretation. Okay, now let's go to weight. We are going to look at weight and then age. First of all, these are numerical values. Look at weight. Okay, this is weight. The coefficient of weight is negative 13.55. We then look at age. The coefficient of age is that. How do you interpret weight? You always start with on average, because a regression is an average measure. On average, giving all the independent variables. And normally, I tell people to mention them all. That's what I normally do. Mention them all, the rest. But the way you mention the dummies, don't mention the dummies one by one. So watch the way I'm going to interpret with. So on average, giving item feasibility, item MRP, age, item fat, item type, outlet size, location, and outlet type, a 1 unit increase in the weight of the item decreases the sales by 13.56 units. On average, given visibility, MRP, age, fat, item type, size, location, and outlet type, a 1 unit increase in the weight of the item decreases the sales by 13.56 units. Now, normally when you are writing this thing in a thesis or paper, you say that ceteris paribus or holding all other factors constant. No, I want you to mention all the other factors. And watch the way I did it. The negative here is the reason why I said decreases. And when you look at the dummy variables, I did not mention each one of them. I said item type because it's all of these are item type. So you don't need to mention each one of them. So when it comes to size, all of these are size. So you don't need to mention all of them. It just says given size, given location, put together, given outlet type, put together. And that is how you got to interpret them. Good. Who can interpret the coefficient of outlet age? This is negative 745. Who can interpret that for us? Who can go by the same way I just did? Samuel, it's a good try you're about to do.
Yeah.
It's good. I like people who try.
On average, given item weight, item visibility, item MRP, item type, outlet size, outlet location, and outlet type, a unit increase in outlet age would decrease sales by 745.78 units.
Excellent. But you missed something. Who can dictate what he missed? You did well. I won't lie to you. But you missed something. Who can dictate that? It's going to be quite difficult for somebody to really dictate that unless you were paying attention. Who can dictate that? Now, that person must be really smart to dictate that. Nobody. That's a shame. Well, you didn't mention item fat content.
Oh.
And I think probably it's because maybe I may have missed that too. Yeah, just maybe. But you didn't, because I was really looking for a loophole in yours. You were not looking for a loophole in mine. Okay. But that is it. You did very, very well in explaining this. This is a numerical variable, and the way you've interpreted it is excellent. Now let's look at the dummy variables. Okay, those that are not numerical. So you have, let's look at small outlet type. That's what we are going to interpret, small outlet type. Now remember that if you look at the outlet type, did I say outlet type or outlet size? Let me just go back. small outlet size, yes. If you look at outlet size, it's here. Okay. And it's not numerical. It's not numerical. Okay, this is small outlet size. It is a dummy. It is a dummy. But before you interpret this, you got to know all the other outlet sizes. Do you remember that one of them is not brought here? Who can remind us of which outlet size is not here? There were 3 of them, if you can remember. Now, one of them is not shown here. In fact, any time you are doing the dummy, one of them is omitted in the regression. Which dummy size, dummy level was omitted in the outlet size? Okay, so let me just show you something. If we go to the results here, when we're looking at size, okay, let's quickly go to the size section. That's it. So you see I did some contingency table here, and you can see the different sizes. We had small, you had medium, and then you had high. So now you can see the high was omitted. Okay. So that is the one that is not showing here. So you're about to interpret this, but you must have that reference category at the back of your mind before you start the interpretation. It's very important. It always carries 7 marks for me. So I'm going to interpret this for outlet size for small, and then you will learn from that to do the others. So let's start. So we start by saying that on average, given item weight, item feasibility, item MRP, age, okay, item fat content, item type, outlets, no, you don't mention outlet size, item type, outlet location and outlet type, sales is predicted or expected to be 762.63 units less if the outlet size is small than high. If the outlet size is small than high. If the outlet size is small than high, sales is predicted to be 762 units less if the outlet size is small than high. Even though high is not here, you know that high is a reference category. So anytime we mention small, it is in reference to high, which is not shown here. So you must have the reference category in your mind anytime you are talking about the others. Is critical. Is critical. That is how you interpret a particular dummy. And when you are doing for medium to, you say the same thing. And watch it. In this definition, in this interpretation, I didn't say that a 1 unit increase in small. No, you can't say that because a dummy doesn't increase or fall. A dummy variable is a static variable. It's not dynamic. It's not dynamic like weight. It's not dynamic like visibility or MRP. No, it is fixed. Dummy is fixed. So if you are within a year at least. So it's very important to not make it like it's changing, but rather the sales is going to be this number more or this number less if the size, the outlet size is small than the reference category, which is high. And that is how you interpret this. It's very, very important to recognize that. Now, let me see whether somebody can interpret this one, which is outlet type, outlet type. Let me see. And then supermarket type 1. Okay. Let me focus on one of them, not both. So let's say supermarket type 1. Now watch it. Supermarket type 1. Before you can interpret this, you must know the reference category for this outlet type. What was a reference category? Do you all remember? Somebody might remember. What was a reference category for the outlet type? I remember. But do you remember? So normally your contingency table will always help you with some of these. This is one thing doing the regression. There's another thing making sense of all of these things that we are doing. And making sense of all of these things we are doing is much more powerful than anything else. Okay, so who has it? To do this, and I know it's grocery, but then let's go and check. Okay. If you go to that, if you want to even change your supermarket, but one way you will know your supermarket is by looking at the entire data set. An entire data set might hide one of them. So it's not also too great to look at the entire data set like that. For example, when you look at supermarket for the outlet type, you see, grocery is there, but maybe in the first 10 rows, grocery might not show. Okay. So one thing you can do is use the contingency table. So I'm going to just use this contingency table here. So you have item fat content and then outlet size. So instead of outlet size, I'll just put in outlet type. Okay, and you run this. Look down here, the results here is going to change. Good. So you see that it brings out all the outlet type. And you can see that the first outlet type is grocery store before supermarket 1, 2, 3. So grocery store is the reference category. So you see, you must have that at the back of your mind before you go to the interpretation of the result. So with that in mind, who can interpret outlet type supermarket known as type 1? Who can interpret that? Let me see whether we have a great person among you. The super person, the protagonist among all of this. Who can interpret the supermarket type called type 1? Samuel, are you thinking? Yes, Samuel, go ahead.
Okay. On average, given item weight, item visibility, item MRP, outlet age, item fat content, item type, outlet size, outlet location, the sales would increase.
No, you missed that part. Remember I said that dummies don't rise or fall. So you should say the sales is expected to be.
The sales is expected to be 1,516.25 units higher if the outlet type supermarket type 1. Sorry, if the outlet type is supermarket type 1 than grocery store.
Excellent. Excellent. You did it. You did it. You cracked it. Now that is how you interpret it. That is how you do it. That is how you go. That's how you try. That's how you break all spines. So that is a very good way of interpreting. Normally, when you have done this, then you now mention, and this is significant. And the way you mention whether or not this is significant is you come and check the p-value. You say, and this is also significant. Then you conclude your work. If it is a project or thesis or dissertation you write. But if it is an exam, like exam is what you just did here. So guys, you should learn how to do interpretation because when you see your exam, you're going to have a lot of these things and you're going to interpret a lot of them as well. Very good. So that is interpretation. Do not miss it. Do not miss it one bit at all. Let's go to the very last two things. Now, what is the distinguishing difference between the p-value and the confidence interval? Now, the p-value, we've said it multiple times, the p-value is the error, expected error. Sorry, the actual error that you make when undertaking any analysis. So the analysis here is a regression analysis. When you're taking the regression analysis, the p-value is the actual error. And this actual error, p-value, is compared with the expected error, which is alpha. And the expected error is usually 5%. And so you normally want the p-value to be less than the alpha for you to reject the null hypothesis of no significance. Now, when the p-value is less than the alpha, the confidence interval, because remember the p-value, if it is 5%, it means that the confidence interval is 95%. If the p-value is 1%, the confidence interval is 99%. So if the p-value is less than alpha, it means that the variable is significant. And in that case, the estimate must be in between the lower confidence interval and the upper confidence interval. We're going to check that pretty soon for you to appreciate it. So the estimate, when I say the estimate, I mean the coefficient. The coefficient of that independent variable should fall between the lower and the upper confidence interval for the variable to be significant. So in short, you can use a confidence interval to determine whether a variable is significant or insignificant. It acts like the p-value. It's just 1 minus the confidence interval gives you the p-value, and 1 minus the p-value gives you the confidence interval. So now let's take an example. Okay, let me quickly go to item weight. Guys, if you check item weight, is it significant or insignificant? Is it significant or insignificant? Item weight. That's its p-value. So is it significant or insignificant?
Insignificant.
All right. So that is insignificant. Now, you can see the confidence interval for that. It is negative 108, positive 81. Okay, negative 108 and positive 81. Okay, so I need to check which confidence interval is being used here. It appears that this one doesn't use, the range of what is indicative. Let me check this last one here. Okay, so unlike R, this one doesn't give the range. It still makes it fall between, even though it is insignificant. Okay, so but the key point is that you use that range to determine whether a particular independent variable is significant. It appears that R does it better than this very one. But as long as the p-value will do the work, you don't need to use the confidence interval here to make the big difference. So please use a p-value for this very software purpose. My last but one question is the specification of the regression model. And you will be asked to do that in all spheres of your career here. Specify the regression model. In specifying the regression model, you will be expected to use the same values that you are using for your work. So when you go to your data set here, you will see that the name of the output is item outlet sales. So guys, watch what I'm about to do because this is very important. So when you are writing, specifying the model, remember the model is a representation of reality. So if you want to write a regression model, you bring the dependent variable first. So you write item exactly as it is. You don't change anything. Underscore outlet underscore sales. Of course, this very one, you can see that it is quite a lot to write because you could have simply said sales, but then you're just using exactly what was given to you in the Excel. Then that is a dependent variable. Then equal to, you bring your beta naught plus, bring your beta 1. Then you write the first independent variable exactly as it is. When you go to this result, the first independent variable is item underscore weight. So you write beta 1, then item underscore weight. Then you do plus beta 2, write a second one, and that is item underscore visibility. It's very annoying, but you got to keep going. Visibility. Then you do plus beta 3, you are specifying the modulo. The next one is item underscore MRP plus beta 4 outlet age. So you write outlet age. Age is capital, so you maintain as capital. Plus beta 5 item fat content. Okay, plus beta 6 item type. You write that. Plus beta 7. Oh, no. Item type bread. Okay, so when it comes to the specification, here you have to write all of them. Okay, so the item type is start with bread. So you got to write item type bread plus beta 6 item type days plus beta 7. After the bread, you have breakfast. So breakfast, you do item type breakfast plus beta 8 item type canned. So you write all of these as long as they are. So if these values are how many? 20, you're going to write all of these 20. Then you add in the end plus the error term. This is the specification of the regression model. So anytime you're told to specify the regression model, just come to your result and you just write them all. Please learn to do that because that is what you do. And that is a specification of the model. Remember that we are only using the betas to represent the coefficients we don't know. Once you know the model and they now know the coefficient, then the question will not be specify the regression model, but rather write the estimated regression equation. Write the estimated regression equation. And you see, that one, you are going to replace these betas with their actual numbers. So if you look at the first beta was, the coefficient was the constant. That's a beta naught. And the constant is 189. So you would replace this beta naught and replace it to 189.68. Just use 2 decimal places. And then the second one was iter time weight. Iter time weight is negative, so it becomes negative 13.56. Then you add item weight to it, item weight. Then continues like that. That is the estimated regression equation. But then the specified model is in betas. The estimated equation is in numbers and then the letters. So that is a key thing. Now, which one do you use for the prediction? You use the estimated equation for the prediction. Okay. Now, I'm not going to, like I said, let me clean this. I'm not going to do all of this with you, okay? But the estimated regression equation is very important. So you will notice that next week, after we have taken care of all the diagnostics, the estimated equation will be something like this. Let me see whether you have it here. This will be your estimated equation because we would have solved a lot of things from the data. We would have even taken the log of some of the variables. And this very thing you see here, okay, this very thing that you see here, this will be, what you see here will be your estimated regression equation. And please note that the estimated equation has no error term. So in the end, you don't add the error term. No, you don't do that. But it carries the letters and the numbers. It carries the letters and the numbers in the estimated equation. And when you want to do prediction, you use the estimated equation to do your prediction. That is what you use for prediction. You shall look at prediction next week because I will ask you to do prediction all the time. In your assignment, you also have prediction to do. So take note of how to write the estimated equation and how to use it to do prediction. What you are seeing here is going to be properly explained properly next time. Okay. So, ladies and gentlemen, that brings us to the end of the entire caboodle for today. For today, what you've done is you've learned how to clean data and estimate regression, how to interpret the scores that you have, okay? And then how to specify the model because the specification of the model is important. Next time, what we are going to do is we're going to look at the problems in the data, in the final way. Okay? We're going to look at all the problems within the final way. Oh my goodness, who's talking a lot like that? I close the person keeps talking. I close the person, let me mute everybody. Let me mute everybody, and then if you have a question, you can raise your hand. So we are going to check for residual to see whether the residuals are normally distributed. We are going to do that next time. We're going to check whether the independent variables have multicollinearity and how we solve that. And you will see that there's multicollinearity problems and we'll solve it. These are called regression diagnostics. We're going to check whether there is homoscedasticity or heteroscedasticity in the model. It is the longest word in econometrics, 18-letter word. So when you're mentioning it, you have to drink lots of water. Then we'll check for autocorrelation. We'll check for outliers, and we'll try and solve these issues that might appear in a regression. And that will lead to that smaller regression result that I gave you. And you will see that after solving all of these, okay, this is the final regression result. Where is that? That you will see this one here. So all our regression eventually will boil down to something like this. Very, very tiny, very, very tiny, which is the most important regression that you would have done in this context. But before we get to that level, okay, before we get to that level, you need to understand the diagnostics of the data set. Okay, so ladies and gentlemen, that brings us to the end of the entire caboodle. We'll meet again, but now I know you may have a question. If you have a question, this is a time you can raise your hand and ask all of it.